Welcome to the session on modelling in mechanics, modelling assumptions. The objectives for this session are to understand and apply common assumptions in real life to mechanical models. Modelling assumptions help simplify and allow analysis of real-life problems using mathematical methods. It is important to understand different modelling assumptions and how calculations are affected by a particular problem. Let's take a look at a model. For example, a particle. We're going to assume that the object dimensions are negligible. So the modelling assumptions that we're going to make are that the mass of the object is concentrated at a single point. So a large particle essentially is treated as a small point. We also ignore rotational forces and air resistance. Let's now consider a rod. All the dimensions except for the pole or beam are negligible. So our modelling assumptions are that the mass is concentrated along the line and that the rod has no thickness. Also, it does not bend or buckle. In fact, it is rigid. Now let's consider a lamina. This is an object which is like a sheet of paper, so has area but negligible thickness. The modelling assumptions we're going to make are that the mass is distributed across a flat surface. Now let's look at the model of a uniform body. This has an even distribution of mass. The modelling assumptions that we make are that the mass of the object is concentrated at a single point at the centre of the object. This is called the centre of mass. So suppose this is our object. This point here is the centre of mass, where the mass of the object is concentrated for our modelling assumptions. Suppose we're considering a light object. This is a small mass of object compared to other masses such as a string or a pulley. The modelling assumptions we make are that we treat the objects as though they have zero mass, and the tension is the same at both ends of the light string. An inextensible string is a string which does not stretch under load. So the modelling assumptions we make are that the objects connected by a taut inextensible string have the same acceleration. For a smooth surface, the modelling assumptions that we make are that there is no friction between the surface and any object on it. For a rough surface, i.e. a surface which is not smooth, the modelling assumptions are that a frictional force is experienced by objects in contact with the surface if they are moving or acted on by a force. A wire is a thin length of rigid metal. The modelling assumptions we make are that it is one-dimensional. For a smooth and light pulley, we consider that all pulleys are to be considered as smooth and light. So the modelling assumptions are that the pulley has zero mass. We also say that the tension is the same on both sides of the pulley. A bead is a particle with a hole for threading on string or wire. The modelling assumptions we make are that the bead moves freely along a string or wire, and the tension is the same on both sides of the bead. A peg is a support which suspends or rests a body. The modelling assumptions we make are that it is fixed with 0 dimensions. It is also considered rough or smooth depending on the question. Air resistance. This is the resistance experienced by an object as it moves through the air. The modelling assumptions we will make are that this is usually negligible. Gravity. This is a force of attraction experienced between all objects. Acceleration due to gravity is denoted by g. The modelling assumptions we make are that we assume all objects with mass are attracted towards the Earth. The gravity of the Earth is uniform and acts downwards. Also, gravity g is constant and assumed to be 9.8 meters per second squared, unless otherwise stated. Now let's take a look at an example. An ice puck slides across the ice after being hit. State the effect of the following on any calculations using this model. A. The ice puck is modelled as a particle. And B. The ice is smooth. So let's solve part A first. Given what we've just looked at, we ignore the rotational effect of any external forces acting on it or on the puck and the effects of air resistance. And now for part B. The ice is smooth, so we ignore friction between the ice puck and the surface. This is an application of what we've just learnt to a real-life problem. This brings us to the end of this session. If you have understood its contents, you should be able to understand and apply common assumptions in real life to mechanical models. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.